Welcome to the final presentation for Design for Manufacturing ArborPress team, Darren, Will, Krishna, Santosh, and Aman. We'll quickly remind everyone what was covered in the midterm report. Product description, we chose to do DfM on an ArborPress. It's a small hand-operated press used for staking, riveting, any small application that you would provide force. Primary customers are machinists, machine shop owners doing low volume fabrication. Secondary are hobbyists using it in the home or small business. Fast diagram, primary functive is press part, followed by apply force, stabilize part, and apply leverage. You can see our exploded view on the left, 14 parts when not counting fasteners and washers. Two assembly sequences we considered were top down and bottom up. We chose bottom up as it was better in several categories when doing the sequence analysis. Shown here is our mapping matrix of which functives are connected to which components. Here's our BOM and total cost of, total cost was $224.19. Quad chart indicated that several components could be redesigned: the base frame, press plate, shaft cap, and gear rack, as well as some other components could be eliminated or kept as is. Functional differentiation, different for each customer group. We have provide, handhold, produce rotation, and create moment. That led us to have module components, the knob, handle rod, and handle shaft, which led to these two designs for our primary and secondary customer. One is a handle rod versus the hand wheel. Again, shown in CAD here, the difference between the primary and secondary customers. Once again, seen in the family product family design diagram, where the variant changes based on the components. Moving on to design for manual assembly and design for automated assembly, you can see our, starting with manual assembly, total assembly time for all 17 components is 147 seconds. We decided to select the frame installation for our platform assembly step, taking a total of 20 seconds. As evidence from our quad chart, which we indicated as a redesign, the two functions of the frame and base are ensure levelness and allow portability. For our module assembly step, we chose the handle rod subassembly, which took 8.6 seconds. Quad chart, we listed as keep as is. It has three functions: produce rotation, create moment, and provide handhold. Platform redesign, we just decided to combine the frame and base into one part, apply the 3 DFA principles, reduce part count, reduce fasteners, and avoid adjustments. For module redesign, we decided to go with a more ergonomic knob, should increase hand access and facilitate orientation to principles, as well as adding a chamfer to the rod, which should increase ease of insertion for manual assembly. Our total time with these changes got down to 103 seconds. For total cost reduction, we went from $2.45 to $1.72, which is a 30% overall cost reduction for the manual assembly. Our assembly efficiency, as calculated in the equation shown below, is around 41%. You can see the CAD model of our after design shown in this slide. For design for automated assembly, we chose our gear system, which is made up of the shaft cap, spur gear, shaft nut, and a washer nut. The quad chart had us keeping as is and eliminating several of these components: function, generate torque, create translation, enable rotation. Our overall cost for total assembly based on the time hand calculations before redesign was $2.11. We incorporated these DFA principles shown in the before and after CAD models below to get a total of just $1.76 total assembly cost for design for automated assembly. For process selection, we chose to redesign the knob, which was redesigned and designed for manual assembly, and the shaft cap, which is redesigned for design for automated assembly. For the knob, we show the cross-section drawing up above, critical dimensions being the overall width, which creates an additional torque and moment, as well as the curve of the handle, as one of our functions was to provide handhold, provide grip for the cranking, which enables the pushing of whatever you have laid out on your arbor press. For tolerances, we chose something not too aggressive because this is a injection molded part of 0.025 plus or minus millimeters. For process selection on this knob, obviously it's going to be a thermoplastic. We decided to go with nylon shape. You can see our process mass chart, process section thickness chart, process tolerance chart, surface roughness chart, and economic batch size chart. All this led us down to the candidates of blow molding, injection molding. The batch size hinted that we should use injection molding, so we didn't have to pay the large fixed costs of blow molding equipment. For the shaft cap, functions being enable rotation, prevent translation, ensure levelness, we redesigned to eliminate some parts. As mentioned earlier, for process material matrix, we chose non-ferrous metal, circular. You can see the mass chart and section thickness chart based on our CAD model information, and then tolerance and surface roughness chart was selected as well, getting us down to the candidates of die casting and machining, with us choosing machining similarly because of the batch size. For the design for injection molding, given the inputs shown above, we got a total cost of $4.11 per part. Then we plugged the knob into DfM Pro and decided to make a few adjustments based on their suggestion, as shown in the image, decreasing the base width, as well as adding draft angles in several locations and decreasing wall thickness. That was able to drop our total cost to $2.61 upon redoing the calculations with different dimensions, reduction in length and width, and overall volume. So we also then took the knob and plugged it into Protolabs and discovered nice reduction, both from our hand calc and from our Protolabs results in overall after redesign costs. Our second DfM for machining hand calculation was $3.50 per part. We used these DfM principles listed and made adjustments using the DfM Pro software shown in these before and after pictures. The DfM Pro got us actually an increase of about 20 cents to $3.73 per part. And even though the manufacturing costs increased, the redesign should help with stress to, I guess, prevent part maintenance, as well as increase durability and manufacturability. Here's also our comparison to the hub's results for cost per part. For designer of product service system, considered a couple things. First, a year-long warranty to replace several components, including the gear rack and ram head if damaged, which should save customer money and reduce waste. A website or a forum to help showcase customer parts and things that people made or maybe 3D printed, and also highlight upcoming versions of a new arbor press. Should help modularize product architecture and save customer money. And lastly, service package for machine shops, which are our primary customer, to allow them to set up a pay per minute system with it would be a lock and unlocking mechanism and payment system for them to increase shared use and provide services to people accessing their machine shop. Conclusions: total cost reduction through DFA $7.72, through DFM $1.26. When you calculate for the whole production year, it's about $700,000. Some critiques of ourselves: we took away some of the ease of maintenance and part replacement capabilities by doing some of the redesigns. The knob redesign also had minimal benefit, and if we were to start over again, we would include some DFM around removing the front plate that could help get rid of poor fasteners. That is all. Thank you very much.